Welcome back. So far, we've been talking about different applications of combinatorics. We've talked about permutations, about combinations, the binomial coefficients, and counting different things using them. And today, we want to talk about the last application, which is going to be a little different. We're going to show that beyond combinatorics, we can use what we have learned to get some results on algebra, and specifically on ways to write a number as a sum of integers. And we're going to show that we can get a simple derivation for what might otherwise be an unintuitive result. So we're looking at counting sums, and specifically we want to find a number of ways to write 5, for example, as the sum of 3 positive integers when order matters. So let's see what we mean. We can write 5 as 3 plus 1 plus 1, or as 2 plus 2 plus 1, or as 2 plus 1 plus 2, or 1 plus 3 plus 1, 1 plus 2 plus 2, and so on. And we can see that these are the only ways to write 5 as sum of 3 positive integers, because if we start with 3, they have to add 1 plus 1. If we start with 2, then we have to have 3. And these are the only way to write 3 as a sum of 2 positive integers. And if we start with 1, then we need to get to 4 with 2 integers, and these are the only ways to do that. So we can see that the total number of ways of writing 5 as a sum of 3 positive integers is 6. And we would like to derive this number 6 combinatorially. So what we can do is we can show that this number of ways is the same as the number of ways to partition 5 items into 3 groups when the order matters. Okay, so we'll let our 5 items be 5 stars. And when we write 3 plus 1 plus 1, that will correspond to partitioning these 5 stars into 3, and then plus 1, and then plus 1. And 2 plus 1 plus 1 will correspond to partition here, which has 2 stars plus 2 stars plus 1 star, and 2 plus 1 plus 2. Similarly, we have 2 stars plus 1 star plus 2 stars, and so on. Okay, and we would like to use this analogy to find the number of ways to write 5 as a sum of 3 positive numbers. So let's maybe reflect a little bit on the analogy. So let's look here at what are the similarities between the addition that we have here on the left and the partition on the right. So in the addition, we look at things that sum to 5. And similarly, for the partition, we look at 5 stars or 5 items. We're partitioning 5 items. Just like here, we're writing things that will sum to 5. Okay. For addition, we have 3 positive terms. Okay. And what we have here is we have 3 consecutive star intervals. So here we have an interval of 3 stars, an interval of 1 star, an interval of 1 star. They have to have at least 1 star. Okay. And for addition, we have 2 pluses, because we have 3 terms, so we have 2 pluses, and that separate the 3 numbers. And here we have, similarly, we have 2 bars that separate the intervals. So these bars play the role of the pluses. Okay, but there's something that we have in the partition that we don't quite see in the addition, and that is, for the partition, we see that we have 4 gaps. So we have 5 stars, we have 4 gaps between them, 1, 2, 3, 4, where we can place the bars. Okay, and this does not quite exist, or we don't quite see it for the addition. So we have 5 gaps between the stars, and in those 4 gaps between the stars, and in those 4 gaps, we need to put the 2 bars that we have. So we need to choose 2 of the 4 gaps to put the bars in them. And so the number of partitions, the number of ways to partition this, is going to be just the number of ways to choose two gaps out of the 4 that we have. And that's going to be just 4 choose 2, which, as we know, is 6. So we see that we could get this number by just looking at the number of spaces or gaps that we have, which was 5 minus 1, or 4, and the number of bars that we have, which was 3 minus 1, or 2, and we have 4 choose 2, which is 6, which is the number that we got here. Now, this, of course, generalizes, and if you want to have k terms that will add to n, then we would like to find how many ways we can write n as a sum of k positive integers when order matters. And so here we have n stars, and therefore we have n minus 1 gaps. And we have k, we want to write them as k, a sum of k terms, so we have k minus 1 bars. They will correspond to the k minus 1 pluses. Okay, So what we want to do is we want to place k minus 1 bars in n minus 1 gaps. Okay, and the number to do that is just n minus 1 choose k minus 1. Okay, so this is the number of ways to write n as a sum of k positive integers. It's n minus 1 choose k minus 1. All right, so let's do a couple of simple examples just to make sure we agree with the formula that we had. And just to remind us, it said that if you want to write n as a sum of k positive integers, when order matters, then we can do it as n minus 1 choose k minus 1 ways. So let's look at some simple values of k. We'll look at the sums and this formula. So if k is 1, then we can write n in a single way as a sum of one term, just n is equal to n. So there's only one term. And sure enough, if we write n minus 1 choose k minus 1, which is 1 minus 1, we get n minus 1 choose 0, which is 1. If we want to write n as a sum of n different terms, positive terms, we have to write 1 plus 1 and so on plus 1. So there's just one way of doing it. And indeed, n minus 1 choose n minus 1. K here is n, so n minus 1 choose n minus 1 is again 1, agreeing with this. If you want to write n as a sum of two terms, then we can write it as 1 plus n plus 1 plus n minus 1, or 2 plus n minus 2, and so on up to n minus 1 plus 1. So we have 1, 2, n minus 1 way of doing it. And if we write n minus 1 choose 2 minus 1, it's n minus 1 choose 1, which is n minus 1. And last example, if we want to write n as a sum of n minus 1 terms, then what we'll have is we'll have n minus 1 terms. One of them will be 2, and the remaining n minus 2 will be 1. So the 2 can appear at the beginning, the second location, or the last location, and the n minus 1 way of doing it, right? Because we have n minus 1 terms. So the n minus 1 place the 2. And if we check n minus 1 choose n minus 1 minus 1 is n minus 1 choose n minus 2, which is the same as n minus 1 choose 1, which is n minus 1 again. So we get that in all those cases, this formula gave us what we expected. And in fact, we can use this formula even when this summation is not easy to find. For example, if I ask you how many ways can write 8 as a sum of 4 positive integers, it might take you quite a bit of time to find all the summations. But you can use the formula. I'd say it's 8 minus 1 choose 4 minus 1, which is 7 choose 3, which is 7 times 6 times 5 divided by 6, which is 35. Okay, easy. And let's extend this result slightly. So suppose we want to write n as any sum, namely we want to find the number of ways we can write n as a sum of any number of positive integers, not a specific number k. Then, for example, we can take n equal to 3. We can write it as 3 itself, or 1 plus 2, or 2 plus 1, or 1 plus 1 plus 1. And these are the only ways we can write 3 as a sum of positive integers. And we can draw an analogy again with bars and stars. And we can see that the number is therefore 4. And if you want to look at stars, then 3 will correspond to just 3 stars, not partitioned. 1 plus 2 will correspond to this partition, 1 and then 2. And 2 plus 1 will correspond to this partition of the 3 stars. And 1 plus 1 will correspond to the partition of the 3 stars where each one is on its own. Okay, and we can see that the number of ways of writing these bars is we have 2 spaces, and we can either write no bars in the 2 spaces, so we can write have a bar in the left one and no bar in the right one, or a bar in the right gap but not in the left gap, or bars in both gaps. And so what we have is just a number of ways to write any number of bars in those places. So it's the number of really the number of if you want sequences of length 2 that we have, right? This will correspond maybe to 0, 0. This will correspond to 1, 0, 0, 1, and 1, 1. And this number is just 2 to the 2, because we have the option of either putting a bar in the first gap or not, and then the option of putting a gap in the second, a bar in the second gap or not. Okay, and this obviously generalizes to any n. So if we have n stars, then in each gap we can either put a bar or not put a bar. And we have 2 options for each gap. So the total number of options we have is 2 to the number of gaps. And we have n minus 1 gaps, so therefore the number is 2 to the n minus 1. Okay, and you could have gotten this number well, like we did here, or you could be a little bit more macho if you wanted, and you could say, okay, this is the number of ways to write n as the sum of any number of positive integers. So I could see how many ways I can write it as the sum of one integer, two integers, and so on. So we can write it n as a sum of k integers, where k goes from 1 up to n. And we know from from the previous slide that number to write it as sum of k integers is n minus 1 choose k minus 1. So we can say that this number is going to be summation of k going from 1 up to n, of n minus 1 choose k minus 1. But now you see that k minus 1 starts at 0 and goes to n minus 1. So it's summation of I going from 0 to n minus 1 of n minus 1's choose I. And then by the binomial theorem, the sum is just 2 to the n minus 1, agreeing with what we got here. Okay, all right. Now we want to modify the question slightly. Instead of looking at positive terms, we want to look at non-negative terms. So we want to ask how many ways we can write n as a sum of k non-negative integers. Okay, so for example, let's see how many ways we can write 2 as a sum of 3 non-negatives. So we can write 2 as 2 plus 0 plus 0. That's 3 non-negative integers that sum to 2. Or as 0 plus 2 plus 0. Or as 0 plus 0 plus 2. These are the only ways to write 2 as a sum of 3 non-negatives where there is a single positive number. Or we can write it as 1 plus 1 plus 0, or 1 plus 0 plus 1, or 0 plus 1 plus 1. Okay. Now, we can again use the stars and bars analogy, and we see that, by the way, that this number is going to be 6. Okay. Now, using our analogy, we can write this as star star and then bar bar. That means that we have 2. You might remember that the bar plays the role of a plus. So we have 2 and then plus 0 and then plus 0. That's this sum. And 0 plus 2 plus 0 we can represent like that. So we have again 0 plus 2 plus 0. Or 0 plus 0 plus 2, we have here 0 plus 0 plus 2, and here 1 plus 1 plus 1, and so on. Okay. So what we see is that it's very similar to what we had before. Just like before, the number of stars we have is the total number that we're trying to add to, is n. And the number of bars we have is the number of pluses, which is not the number of terms minus 1. It's k minus 1. So I have k minus 1 bars. But unlike before we put a single bar between in each gap. And here we can put multiple bars in a gap like this. We can also put bars to the right or to the left of all the stars. So now we can have any arrangement of the stars and bars. If you write any arrangement of 2 stars and 2 bars, you can interpret it as a sum of 3 terms that will add to 2, right? Because you'll have the number to the left of the first bar plus the number to the in between plus the number to the right, and that will give you 2 because you have 2 bars. Because you have 2 stars. Okay, so therefore we see that every sum corresponds in a one-to-one way. There's a one-to-one mapping between a sum of here on the left and an arrangement of stars and bars. Okay, so now therefore the number of sums that we have is going to be the number of arrangement of stars and bars, and more precisely the number of arrangement in this case of 2 stars and 2 bars. Okay, so so it's number of sums is the number of ranges of stars and bars, and we're interested in the number of ways to order to write 2 stars and 2 bars in this case. And if we have 2 stars and 2 bars, what we have is a sequence of length 4. And we need to choose the location of the 2 stars. So the number of ways to do it is 4 choose 2, which is 6. Okay. And more generally, if you want to write n as a sum of k non-negative integers, so if we want to find the number of ways to write n as a sum of k non-negative integers when the order matters, then we have, again, n stars, and we have k bars, and we can rearrange them in any way we want. So we have a sequence with n star and k minus 1 bars. Or in other words, we have a sequence of length n plus k minus 1, and we need to choose the location of the k minus 1 bars. And that number is going to be n plus k minus 1, the length of the sequence, choose k minus 1, the number of bars we want to choose. And that's the same as saying n plus k minus 1, choose n if you want to choose the location of the bars. That will be the same. Okay, so let's look at an application of this. So let's see how many 4-letter words are there, but now when the order does not matter. So if the order matters, then the number of four-letter words is going to be just, we have 26 ways to write the first letter and 26 ways to write the second letter and so on. We get 26 to the 4, which is almost 500,000. Okay. Now, if we want the number of four-letter words when the order does not matter, then, so for example, if you want things like evil to be the same as vile, to be the same as live, and so on, and words can also have repetition, so doom will be the same as mood, and so on. So the word or the number of words is just determined by the composition. So if I tell you number of A's, number of B's, number of C's, up to number of C's, that will determine this collection, right? Because we don't care. Once I told you the number of times each letter appears, then all words, because order doesn't matter, all words are going to be the same. So what we really want to see is how many such compositions we have, how many ways we can have for deciding on number of A's, number of B's, and so on, such that together they'll sum to 4, because the length of the sequence we want is 4. Okay, so the number of four-letter words when the order does not matter is the number of ways to select the number of A's, number of B's, and number of C's, and so on, so that they sum to 4. And what we have here is just 26 non-negative terms correspond to the letters. So K is 26 in our terminology, and they sum to 4, the length. So N is equal to 4. And that number is, as we know, is N plus K minus 1. So 4 plus 26 minus 1. Choose K minus 1. Choose 25. So it's 29, choose 25, or 29, choose 4, and that's not so difficult to calculate. It's roughly 23,700, it's exactly 23,751. Okay, and one thing that you may wonder is whether this makes sense, that this number is going to be that much smaller than the number of letters or words when the order matters. And you can see that most of the words will have four different letters. And if they have 4 different letters, then if the order doesn't matter, then we just look at the number of words and divide it by 4 factorial. And so most of this 26 to the 4 words will have 4 different letters. And then we need to divide them by 4 factorial to get the number when the order does not matter. And 4 factorial is 24. And you can see that if you divide this by 24, if you divide 456,000 by 24, you'll get a number which is, I think, around 19,000. And what we get here is a little more than 19,000, and that's because we also have words that contains 3 letters and 2 letters and 1 letter and so on. So this makes sense. Okay. And we can see a couple more applications. I want to finish with them, but talk about them a little more briefly. So first of all, you'll notice that we derived the number of ways to write n as a sum of k positive integers. We said it was n minus 1 choose k minus 1. And we can derive that number using the formula that we just had for non-negative numbers. And that's because if you have k positive integers that add to n, the number of such sums of k positive integers that add to n is the same as the number of k positive integers that add to n minus k. And the reason is that if you have k integers that add to n, for example to 7, we can subtract 1 from each number here. So instead of 1 plus 2 plus 1 plus 3, we're going to have 0 plus 1 plus 0 plus 2. And when we do that, we subtracted 1 from each of the k terms, here are 4, so that they'll add not to 7, but to 7 minus 4, which is 3. And you can map every sequence of k positive integers that add to n by subtracting 1 from each number. You'll get a sequence of k non-negative integers that will add instead of n to n minus k. This correspondence is a one-to-one correspondence. So therefore, the number of ways to write k positive integers that add to n is the same as number of ways to write k non-negative integers that add to n minus k. And that number is, as we just saw, is n minus k plus k minus 1 choose k minus 1. And this k's will cancel, which will give us n minus 1 choose k minus 1, which will recover the formula that we got for initially. Okay. Also, if we can derive the number of non-negative integers that add to, instead of n, that add to at most n. And the reason is because the number of k non-negative sums that add to at most n is equal to the number of k plus 1 non-negative sum that add to exactly n. That's written here behind my picture, and to exactly n. And to see that, notice that, for example, if we have here a sum of 3 terms that add to less than or equal to 7, 2 plus 0 plus 3, that adds to 5, which is less than 7, then we can map it to a sum that will add to exactly 7 by adding a number here, which is at least 0. It will be 0 if the number added to 7 initially. And again, this mapping is 1-to-1. I can map every sequence here to a sequence here in a unique way by just adding the number that's missing to make it 7. And in general, if we have k non-negative integers that add to at most n, I can map it to k plus 1 non-negative integers that add to exactly n. And so the numbers are the same, and therefore the number is going to be n plus, instead of k, we have k plus 1 now terms, so it's n plus k plus 1 minus 1, choose k plus 1 minus 1, and that gives us the simple formula of n plus k, choose k. And you can verify it if you'd like for some simple values. Okay, so with that, we're done talking about stars and bars and what I think is a fairly nice application of binomial coefficients. And so we discuss our final application that shows that beyond combinatorics we can apply to other fields like algebra and derive the simple derivation of what otherwise might seem like an unintuitive result. And with this, we're also done talking about the combinatorics. And what we'll do next is we'll start talking about probability. See you next time.